Hello everyone, welcome to the third module in this course on microsensors and nanosensors, and this is our first lecture in this module. Here over the next 5 lectures we will be discussing on various principles of sensing. There are several physical effects which arises due to generation of electrical signal in response to non-electrical stimuli. Okay, in module 1 we have seen that the definition of sensors is like that, right? So something which convert non-electrical stimuli to some electrical output. Okay, so there are various physical effects which can do this, so you can understand this as a principle of transduction also. Okay, so mostly we will be focusing on 5 different stimuli, 5 different physical effects, including capacitance, inductance, resistance, piezoelectric effect and pyroelectric effect. But in this course we will be also using other physical effects like piezoresistive effect, for example, or some optical effect like infrared in the infrared transducers, okay, and some temperature transducers also. We will discuss that in whenever it is needed, okay. But in this physical effect module we will be focusing on these 5 physical effects. These can be used in direct sensing. We have, if you remember, we have seen the definitions of direct sensors and complex sensors. Direct sensors were those where the physical effects can directly convert non-electrical stimuli to some electrical stimuli. Okay. However, complex sensors were also composed of various transducers, like if you remember, we have seen an example of say transducer 1, 2, 3, and then it was connected to a direct sensor. Okay, so I wanted to convert this signal S1 to say signal Sn. Okay, and this was done through various transducers. Like first I have converted this S1 to some signal say S2, and then this S2 was converted to signal S3, and then S3 to another signal say S4, which was input to a direct sensor which gives electrical signal Sn, right? So Sn is a electrical signal, except Sn all are non-electrical signals, right? So most of the physical sensors that we are discussing right now are used in direct sensors. Okay, in today's class we will be focusing on capacitance or capacitive transducers, or physical effect which utilizes change in capacitance. Okay, as we know that many sensors nowadays are based on our capacitive principle. Okay, be it your touch screen of your phone, or a displacement micro displacement sensor, or say most of the humidity sensors, say for example 75% RH sensors are based on capacitive. So this is a very crucial transduction phenomena, or detecting the changes in capacitance is very important in context of a sensor's application. Okay, so it can be applied to measure distance, area, volume, pressure, force, chemical composition, and many other things. Okay, and based on this principle, okay, I can have sensors like proximity sensors, humidity sensors, gas sensors, and all. Okay, capacitances can be calculated by relating potential difference between the plates of capacitance charges, okay, as C equal to Q by V. So if I have a parallel plate capacitor, and if the charge is Q and it is attached to a, or it carries a potential of V, okay, I can say that the capacitance is Q by V. Okay, these concepts has been taught in class 12 or before, but we are still revisiting that in the context of sensors. Okay, so we will see mostly the parallel plate capacitors, and if other capacitors or other configuration is required, we will discuss that. Okay, so capacitance of a flat capacitor in vacuum is C is epsilon naught A by D, where epsilon naught, you know that it's a permittivity of your air, okay, or vacuum in this case. Okay, and this is a typical configuration of a capacitance. So you have 2 parallel plates, it is connected to a say potential, and based on this you have charges on your plates. Okay, and if d is the distance between them and a is the area of your plate, okay, and v was the initial potential, so this capacitor charges to a potential when it equates this v, okay, and that's how you find capacitance, right, epsilon a by d, okay, and this is again shown in the form of a point charge, but all this constitute a single plate, and similarly you have a negative charge this side, and then you have electric flux of lines, okay, fine. So in a capacitive sensor, capacitance value is the measure of a stimulus, okay. So if you see this capacitance, the stimulus needs to change one of the parameter which define the capacitance, and for parallel plate you can see that there are three different parameters, be its dielectric constant, be its area of the plate, be its the distance between the two plate, okay. Say if I take a typical example of a say displacement sensor, for example, okay, I have this two plate, say I am calling it plate A and plate B, okay, and in between I have a dielectric material placed, okay, fine. This plate A is hinged at one place, okay, so A is actually attached to a wall and it is not moving at all, okay, and I am using it to measure some micro displacement, okay. So the object which is moving, okay, the object which is moving, I am calling it M, the movable object, okay, is attached to the moving plate B, okay. Now the movement of B is recorded in the form of several things, be its change in the distance between these two plates, or if this plate is moving this side, some air is coming here, so you are also having the change in dielectric material or dielectric constant, okay. So by this, by calculating this displacement d, and by quantifying the the air or the change in capacitance, okay, you can calculate this C or say delta C, okay. Say if delta C is like initial capacitance was C1 when there was no movement in M in the object M, and C2 is say for example the change in when there is a change in this object's position, okay. So your delta C is C1 minus C2, okay, and based on this you can calculate the relative response of the displacement sensor, okay. So this is just an example. There can be other ways also, say for in this case only if I consider another example, okay, like say if both the plates are fixed, for example, okay, both the plates are fixed in its position, and this is your dielectric material, okay, and say this dielectric material's position, say if one object is attached over here and there is a change in the position of this dielectric material, say let's take its example, okay. So this is the initial condition, this was the say initial condition, okay, and the second condition is it has moved to this place, okay, and now I have something like this, okay. So this area is again being covered by air only, okay. So even though the plates are fixed, okay, the capacitance of this capacitor is changing, okay, and that change is, you can account for the movement of the object M, which is now in place of being attached to plate B is attached to the dielectric material itself, right. So I mean there can be various ways to design a sensor based on capacitive principle, okay. So the idea is if anything is varying, okay, better to vary one of them in a go, so that it is easy to account for. But if you can take care of multiple things changing in one go, okay, you can still make a very good sensor, okay. But please note that these changes should be significant so that the interface circuit, the amplifier or whatever you are using to amplify this signal, okay, it should be readable, Okay, then only, because if you go to module 1 and see the sensors definition was, okay, the output should be electrical, okay, but it should be readable by the next circuit. Okay, next is circuit only. Okay, so it should be readable by the circuit just after that. Okay, so please note that the equation that we have discussed yet till now holds only for capacitance of the parallel plate type. Okay, a change in geometry will require modification in the formulas. Okay, say if you are coming up with a concentric cylinders, or say concentric elliptical kind of shapes, or say rectangular kind of things, okay, things will change. Okay. In this equation, epsilon A by D, please note that the ratio A by D can be called geometric factor, particularly for this parallel plate capacitor. And geometric factor is very important factor, because if you see, this ratio will depend on the geometry, shape, size of the plate. Okay, so if I have to write the capacitance formula, I can simply write as epsilon naught into the geometry factor. Right. So this term we are defining particularly in the context of these sensors. Okay. Now let us see capacitance of coaxial cylinders. Okay. So capacitance of a cylindrical capacitor consisting of two coaxial cylinders, say of radius A and B as shown on the screen, okay, and having length L, which is the overlapping length of these two concentric cylinders, can be calculated by simply this equation 2 pi epsilon naught L by ln B by A. Please note that I am neglecting any fringing effect here. Okay, so I can write this capacitance value as 2 pi epsilon naught L by ln B by A. Okay, here L is the length of the overlapping conductors, and term 2 pi L by ln B by A is called a geometric factor for coaxial capacitors. Okay, for parallel plate we have just defined it to be A by D, right? So A by D was my geometry factor for parallel plate capacitor. Now the size and shape of my capacitor has changed. Okay, it has become coaxial cylinders. Okay, so my geometry factor has changed, but please note that the formula for capacitance remains same. Okay, means C equal to epsilon naught into geometry factor, right? It has remained same. Okay, so but the geometry factor has itself changed, because of course the geometry of the capacitor is changing. So it has become now 2 pi L by ln B by A. Okay, and this is the geometry factor of a coaxial capacitor. Okay, a useful displacement sensor can be built with such coaxial capacitor if the inner conductor can be moved in and out of this outer conductor. Okay, so this relationship can be used for the calculation of the capacitor, or in turn to calculate the displacement, right? Capacitance of such a sensor is in a linear relationship with the displacement L. Okay, now let us understand a bit physics of this capacitor, because this will help us in designing better sensor. But to understand this, please recall the definition of polarization or polarization density. Okay, if you recall, it is nothing but electrical dipole moment per unit volume, right? And the more easily a material be polarized, the greater the amount of charge that it can store when it is used in a capacitor. Okay, so we have seen that for parallel plate capacitance is epsilon A by D. This equation is of course valid for parallel plate capacitor at vacuum or say air. Okay. In 1837, Michael Faraday has investigated the effect of completely filled space between the plate with another material, say which is a dielectric or a kind of insulator. Okay. The effect of the filling is to increase the capacitance of the device by a factor K, and this K is known as dielectric constant of the material. Okay. So now if you want to use another material in place of air, you have to use a permittivity value of epsilon R. Okay. So this or just multiply this with K, right? So K into epsilon naught is actually your epsilon R. Okay. So, as a result of a molecular polarization, there is an increase in capacitance due to the dielectric presence. Okay, in some dielectric materials, like some liquids like water, molecules have a permanent dipole moment, while there are some materials which doesn't have a permanent dipole moment. Okay, but there the molecules usually get polarized by some external electric field, and it is known as induced polarization. Okay, in both the cases, either your permanent electric dipole or acquired by the induction, they tend to align molecules with an external electric field, which is known as your dielectric polarization. Okay, initially there is no voltage between the capacitor plates. All dipoles are randomly oriented, right? So when capacitance exists in its original form, no voltage is applied. Okay, all dipoles are randomly oriented. Okay, so all dipoles are randomly oriented, right? True. Once the capacitance is charged, the dipoles will align with the electric field of lines. Okay, we have already seen the electric field lines in case of parallel plate capacitor. Okay, however, the thermal agitation will prevent a complete alignment. Okay, thermal agitation will not allow these dipoles to align with electric field completely. Okay, most of them will align, but it will not allow the process to complete. Okay, each dipole forms its own electric field and is oppositely directed with the external electric field E naught. So each dipoles will try to oppose the electric field or the external electric field. Okay, something like this. Okay, you have initially, when there is no potential applied, you have all these dipole moments oriented randomly. Okay, then when you apply a potential V, okay, and you have established field of lines, okay, uh, then also ideally they should align, but then there are different tilts that you can see because of thermal agitation. Okay, and this dipoles will also have some associated electric field which will try to oppose the originally existing electric field of lines. Okay, this reduced electric field results in a smaller voltage across the capacitor. V will be equal to V naught by K. Sometime this value, okay, this V equal to V naught by K is also reflected in terms of capacitance. Okay, so C is, we have already seen that if a capacitance is carrying a charge Q, okay, the capacitance can be calculated as Q by V. Okay, so we have C is equal to K into C naught. Okay, right? Or C for parallel plate capacitor, C is equal to K epsilon naught A by D. So we have reached to the same point which we were discussing some time back, that if epsilon r is the relative permittivity of the new material that is being inserted between two parallel, the capacitance will change to K epsilon naught A by D, right? So we have reached to the same point. Okay, usually you will find that for sensing application, most of the time there will be some polymer or some other insulator very specific to that kind of sensor placed in between two parallel plates, and rarely we use air. Okay, because it provides you better control for sensing applications. Okay, so the capacitance between two objects can be defined through a geometry factor G. Okay, so C can be given as epsilon K A by D, where A by D is nothing but the geometry factor. Geometry factor depends on the shape of the objects and their separation. Okay, because it gives you G is nothing but A by D, right? So it takes care the shape, this area takes care the shape, and D takes care of the separation. Okay, it shows that a capacitance can also be modulated by varying the dielectric constant. The example that I have given you for the displacement sensor, where the two plates were hinged at two sides and the dielectric material was moving inside. Okay, there can be other ways also, like this dielectric material itself is changing. Okay, there can be a case where you are replacing this dielectric material with something else, or there can be very interesting other sensors also. We'll try to see some of them. Okay, so dielectric constants must be specified for test frequency and temperature. Okay, some dielectrics have a very uniform dielectric constant over a wide range of frequency. One example is polythene, while others show strong negative frequency dependence, means that a dielectric constant decreases with frequency. Okay, so you have to choose the dielectric material very wisely, particularly by understanding the range of frequency your device is going to operate or your sensor is going to operate, as well as the temperature range where you are going to use these sensors. Okay, mostly the temperature dependence of the dielectric is negative, means same, the dielectric constant decreases with temperature. Okay, so that's why I have mentioned that you should know the temperature and frequency operation for your sensor, right? So usually in the laboratory we use very good capacitor. You might have seen a different kind of capacitors being used in the laboratory. They are called good capacitances. Okay, for sensing application we do not want good capacitances. I will tell you why. Okay, in a good capacitor used in electronic circuits, say for example for your basic electronic lab or for other lab, a dielectric constant and geometry are stable. Okay, therefore your capacitance is not changing with ambient. Okay, ideally they should not vary with temperature, humidity, pressure or any other environmental factors in your laboratory. Okay, say for example you are using your capacitor in say Guwahati, and then again you are taking it to a very humid condition where the humidity is 100%. Okay, that ideally for electronic circuit this capacitance should not change. Okay, otherwise the measured value will change. Okay, however, to design a capacitive sensor, okay, we need to make a bad capacitor, okay, whose value varies with the ambient condition, particularly with temperature or humidity or pressure or any other parameter that I need to sense. Okay, say for example, consider a say pressure sensor. Okay, I have say two plates. Okay, and say one plate is again hinged. Okay, and I want to exert some pressure here by which this D is changing, this D value is changing between two plates. Okay, the condition that this plate is not touching this plate but it is compressed to certain value. Okay, it can be by various means. Say the second plate, for example this plate B, I can make say made up of say kind of very thin film, okay, or kind of membrane. Okay, so in that condition, say I'm plotting it horizontally. Okay, say this is the condition. Okay, this plate is fixed. I'm plotting the same thing here. This plate is fixed. However, I'm pressing this plate B and it is changing its shape. Say this was very thin membrane, for example. Okay, by this I'm changing this D value, right? Initially say it was D, now it has become D dash. Okay, the good capacitances that I just discussed for electronic circuit should not change this D value. It should be rigid so that by pressing this D is not changing. But if I want to develop a sensor based on this capacitive, you know, D should be changeable and the capacitance should be sensitive enough to measure any small deflections also. Okay, so it should be as bad as it can be. Okay, so that is the difference between a sensor and a simple electrical units or electrical components. Okay, we are discussing the same capacitance but in different perspective, and perspective is totally different than electronic circuit or a simple electronic course, where I am looking for a capacitance whose value is not changing in the ambient. However, for sensing application, we are looking for entirely different class of capacitor which is changing by applying some external stimuli. Okay, it can be humidity if it is a humidity sensor, it can be a pressure, it can be a temperature or any other parameter. Okay, so by allowing a capacitor's parameter to vary selectively with a specific stimulus, useful sensor can be designed. Okay, let us consider one example of capacitive water level sensors. This we are seeing in a quantitative way. Okay, I will also give some example in a qualitative manner. Okay, let's consider this figure which is a capacitive water level sensor. Okay, say till this point I have a water, and this is your conductors. Okay, now the sensor is fabricated in the form of a coaxial capacitor, as you can see over here. Okay, a surface of each conductor is coated with a thin isolating layer to prevent any electronic short circuit in the water. Okay, please note that isolator is a dielectric, but it is not considered here as it does not change the process of the measurement. Okay, so now this concentric coaxial capacitor is dropped in a say water container. Okay, now I have formed two different capacitances. One capacitance C1, which is say capacitance of the water free portion. This is water free portion. Okay, and C2 is capacitor of the water filled portion. So I have made two capacitors in this flask, or say tank. So if I want to calculate the capacitors, I can write C1 plus C2, since C1 and C2 are in parallel. Okay, now for C1, which is capacitance of the water free portion, I have only air present, so I have to write epsilon naught into G1, where G1 is the geometry factor in this area, right? And the second thing is, which is immersed in water. Okay, I call it epsilon naught into K into G2, where G2 is the geometry factor in this area. Okay, we know that for coaxial capacitor, this coaxial kind of coaxial cylinder kind of thing, the capacitance is 2 pi epsilon naught L by ln B by A. Okay, therefore if you calculate, the total sensor capacitance will be 2 pi epsilon naught L by ln B by A into H, which is the total length from the bottom. Okay, minus H into 1 minus K, right? Here L is the empty portion and H is the height over the water filled portion of the sensor. Okay, so if water level is at say or below H naught, the capacitance remain constant. Okay, there are other sensors also which you can design based on this change in capacitance. This is just one example. Okay, now let me give you an example of humidity, because as I have mentioned that 75% humidity sensors are based on capacitive principle. Okay, say consider the same thing, interdigitated kind of electrode. Okay, it will look like planar kind of geometry. Okay, the same interdigitated electrodes that I have used to explain the gas sensors, or let's take an example of gas sensors only using the capacitor. Okay, or the capacitive principle. Okay, this is my transducer, right? Okay, this is simply a interdigitated electrode. Okay, now my receptor now is a insulating material, or it can be a semiconductor also, depending on the temperature or frequency of its operation. Okay, now when some gas molecules interact with this sensing film, what will happen? Okay, it can either physi-jobbed or chemi-jobbed with the sensing film. Because of that, there will be a change in the dielectric properties of the material. Okay, either it will increase or decrease. Okay, say initial capacitance was C1 and now it has increased to C2. Okay, so I will have a quantity, say delta C, which is C1 minus C2. Okay, and I can calculate the response as delta C by C1 into 100, where C1 is my baseline, right? So by this, I think the description of a qualitative capacitive sensor is clear to you. Okay, quantitative description I have given for the water level sensor. Okay, there can be other conditions also, like I have given example of proximity sensor. okay, a pressure sensor, okay, relative humidity. Now in this example only, now just replace this gas molecules with the water molecules, okay. What will happen? Again the same thing, this water molecule interact with the sensing layer depending on what material it possesses, okay. Either you can have electron conductivity or a proton conductivity, okay. Depending on that, the the current levels changes, and because of that this capacitance value changes, okay. So this is just an example that how a capacitor or a simple capacitance principle can be used in a sensing application. Please note that we need a bad capacitances, not a good capacitance that we require in case of a electronic circuit or in case of some other signal conditioning circuit, okay. We'll meet in next class with some other physical effect. Thank you.